Okay, here we are. We're going to finish up our reaction rates and equilibrium uh, lecture. And no chemistry unit would be complete without an actual quantitative way of describing what's going on with the chemistry. And so we have what is called an equilibrium constant. And this is sort of the conglomeration of what all of your concentrations and all of the amounts of all of the things that are going on in your equilibrium reaction, how they know, essentially how Le Chatelier's principle knows when to raise concentrations, lower concentrations, how to react to a tweaked system. So the law of mass action describes the conditions of chemical equilibrium, and it works like this: if we just have a general uh, expression where uh, this right here is our chemical equation, where A is the coefficient, little a is the coefficient, big A is the actual uh, reactant or product. Um, well, actually say that word. Lowercase letters represent the coefficients, and the uppercase letters represent the concentrations of the reactants and products. We get this. We get this expression over here. This K, which is the constant, equals that. And by convention, the products always go on top. So these guys over here always wind up going on the top of your fraction, and the reactants always go on the bottom. So K then is known as the equilibrium constant, and it is through this that you can see, because this number is going to stay the same, that when certain things go up, other things are going to have to go down with our concentrations. So K is temperature dependent. So in other words, if you increase the temperature, then K might change with that. So it'll be K should be given to you with a particular temperature in mind. Now, we never include liquids or solids into the expression, as you can't change the concentrations of them. Okay? They are a constant in the reaction. So if you have, if you just put some sort of solid into your solution, like a lump of, like a rock or something, its concentration is constant, so it can't really change. What can change are things that are dissolved in solutions. Okay, so we only include gases and aqueous solutions in the equilibrium expression. So we're going to make these equilibrium expressions for the following reaction. Okay, so we're going to write this off to the side. Remember that K equals C to C, D to the D, A to the A, B to the B. So we're going to take this template here, and we're going to map it onto this stuff over here. So the equilibrium expression is going to be K equals, okay, our products go on top. That's going to be NO2 to the fourth times H2O to the sixth. We can use it because it's a gas. Usually H2O is a liquid, but we can use this one because it's a gas. Over NH3 to the fourth times O2 to the seventh. And that becomes our equilibrium expression. We could take the concentrations, the experimental concentrations, of all four of these things and plug them in there, and that is going to give us what this K value would be. But you may get one of those in your homework, but you're not going to be expected to evaluate what a K is yet. Okay, here's another one. What is the equilibrium expression for this reaction? I'm going to raise this up a little bit. Okay, the equilibrium expression for this reaction is going to follow the same pattern. Except notice, here's a solid, and from up here, we never include liquids or solids into our expression. So we're going to avoid those two guys, and we're going to make it K equals the products on the top, CO2 squared, divided by concentration of carbon monoxide squared. And that's it. That would be your new K. SNO2, tin 4 oxide, and tin are both eliminated as they're both solids. Okay. So if we reverse the reaction, then the equilibrium expression becomes 1 over K, because if we're looking at, if we have A to the A plus B to the B makes C to the C and D to the D, that if K is the equilibrium expression for that reaction, then the expression for that reaction is just going to be state is going to be A to A, B to B, or C, D, D, because if we're going back this direction, these guys become the products, and these guys become the reactants, and so these guys would go on top, these guys won't go on bottom, but if these are on top and those are on bottom, that is equal to 1 over K compared to this over here. And so it doesn't really matter which way you do it, it's just really however you write it down is the idea. So what does the value of K mean? Well, we're going to explore a couple of things. One, if K is less than 1, that means equilibrium. Well, you tell me. Okay, in fact, we're going to erase all of this stuff and start examining what exactly this equation means here. If K is less than 1, okay, so we're going to ignore this right now. So if K is less than 1, then if K is less than 1, then the equilibrium, so if K is less than 1, that means the denominator has to be bigger than the numerator. So if this is going to be bigger, that means these are going to have higher concentrations, and so the equilibrium is going to be shifted to the no. Equilibrium is going to be shifted to the left, which is going to be where the A and the B are. Okay. Now, if K is greater than 1, that means our numerator is going to be larger than our denominator, and so the C and D, the product concentrations, are going to be bigger, and it's going to be shifted to the right. Now, if they're equal to each other, if K equals 1, that means the equilibrium is about halfway between the reactants and products. Now, there's one more little piece I want to talk about, and I want to talk about Le Chatelier's principle based on the K. So, here's the idea. We have, okay, so if we move our equilibrium constant down to the bottom of the page, I want to talk about Le Chatelier's principle. Le Chatelier's principle in terms of our equilibrium constant. So remember that this equation is a to the a plus b to the b reversible with b to the c plus d to the d. So if we were to increase the concentration of A, okay, look at how this is going to affect all of the other things on here. If we increase this one and this stays the same, either B is going to have to go down, okay, to maintain the same constant, or C is going to have to go up, or D is going to have to go up in order to counteract what A is. Okay, or we can try it a different way. Let's say we want to let's say we want to decrease the concentration of D, or the stress we put on the system is a decrease in the concentration of D. Then what the other guys are going to do, B, in order to keep K the same, this number is also going to have to go down. Otherwise, K would decrease. If we drop this one, it'll keep K the same. Or A would have to decrease, or some combination of both. That's okay. Or C, if D goes down, then C times D would have to stay the same, and so we would want C to increase. Now, all of Le Chatelier's principle is wrapped up. All of Chatelier's principle is wrapped up in this idea here that the four concentrations, or all of the concentrations in your equilibrium, are trying to maintain a constant K for the equilibrium. And so no matter what happens with Le Chatelier's principle, no matter what happens over here, this K is always going to stay the same, and it's going to be arranged with these four concentrations. So when we start doing the Le Chatelier's problem, start doing homework, refer to this and keep this in mind in the relationships. And that's it.